Okay, Ji, let's get started for today's lecture. We are in week number 10, and the topic we are exploring is recurrent neural networks, right? We had seen some basic introductory level concepts which are related with recurrent neural networks, that what are the different applications, right? And today we'll be extending the same discussion. But before that, I'll just give you a quick recap of what we were looking at. So I think this was the last discussion that we have had in the previous week, that basically a recurrent neural network is just like any other neural network. The only difference is that when you are feeding an input, right, to the neural network, this is just like any other input. In addition to the current input, right, you also take some information from the previous time step, right? So you see, we are at the third timestamp, so we are feeding the third input, which is x3, but we are also taking into account that what was the what did we have at t equals 2. So you can assume that this is your time axis 1, 2, 3. So not only you are looking at the current input, you are also getting some information from the previous time steps, right? So this was the general idea, and you can easily relate it with the applications, that mostly when we have sequential data, we feed it one by one to this model, right? So this part is just like a neural network, nothing different. The only difference is this arrow which is coming from the left side, which is some information from the past, right? So otherwise it's almost the same idea. And we had arrived at these expressions, right, that whenever you see this arrow, so this arrow is actually uh, a fully connected architecture, right? So if you have some input, maybe I have written x, but here I will have some certain number of neurons, right? Say 5 neurons. So these 5 neurons are actually connected to these 4 neurons in the hidden layer. So you will have a weight matrix of 4 by 5. Okay. We'll see in the next slide, we'll see in detail how to compute these matrices. So the expression we derived was that, to generalize, we say that your current input, which is xt, it is multiplied by a weight matrix. So this is the weight matrix, which is this one, which is on the this vertical arrow, right? Then you have some information coming from the previous timestamp. So you have a t minus 1. It is also multiplied by a weight matrix. So this is the weight matrix which is on the horizontal, you can say, arrow, right? And then you add a bias. So you add all of these together, you apply some activation function, so you get this activation for the next, you can say, next timestamp, which is at. Similarly, if you have to compute the output, which is y, so you also have a weight matrix on this arrow, which is coming from this block to the output. So you multiply this with AT, which is the activation of this layer. Okay, so whatever is going on this horizontal arrow, which we are calling AT, the same thing is here. Okay, these are just two branches coming out of the same thing. So it's exactly the same AT which you are computing here. And then you add bias, and you apply another activation function depending upon whether you are solving a two-class problem or a multi-class problem. It can be sigmoid or softmax, right? So mostly for this hidden layer in RNN, we use tanh, and for the last layer, we use either sigmoid or softmax, depending upon the problem we are trying to solve. Okay, so to some extent we discussed this last time as well, but I'll just recall it because this is something important. That you see, mostly we draw an RNN simply by encapsulating everything. We just draw maybe 3 circles like this. Okay, that this is input, this is hidden, this is output, and it is something like this. So in the beginning, it is not very easy to understand things by this notation. Okay, so it's a good idea that we spend some time, and we, rather than just drawing a single neuron, which is encapsulating the complete layer, we draw it the trivial way. Okay, so I have just drawn, say, I hope 10 neurons here. That these are 10 neurons, which is my input. Then this is my hidden layer, and at the output I have 1 neuron. Maybe I'm solving a two-class problem. Okay, so you see, when you are feeding input, so these 10 neurons are actually connected to these 4 neurons, means everything is connected to everything. It would be something like this. And similarly, they are connected to the second one, third one, fourth one. So in total, you have 40 connections. The size of this weight matrix, which we call WAX, A for activation, X for input, it is 4 cross 10, right? Which is the same way, because you have 4 here and 10 here. This is the same way you compute number of or the size of matrix in an MLP, right? Then you have one neuron here and four in the previous layer, so you have four connections, so your weight matrix is 1 cross 4. Okay, so this is basically more like conventional MLP. One additional thing is that you have time on this axis. Okay, so you also have since in the hidden layer you have 4 neurons, so it means I have 4 here. Similarly, the next time step will have 4 and so on. So I need to know how many connections I have in this horizontal direction. So you see, since we'll have the same number of neurons at each time step, so if there are 4 neurons here, I have 4 neurons here, so the weight matrix would be 4 cross 4. Okay, so these are, for example, if I say there are 10 neurons in the hidden layers, and this matrix would be 10 cross 10. Okay, so it is the same concept, but just you can say represented differently. Okay, so now maybe I'll just write some expressions so that you understand them easily rather than directly showing those to you on the slide. Okay, so I'll write very slowly stepwise. So we just said that, okay, when we are computing AT, what are we doing? We are multiplying the previous hidden state with some weight matrix. AT minus 1 is multiplied by this. Okay, then we multiply input matrix with the current input, which is xt. Okay, and then we add a bias, let's call it BA, and then we apply some activation function, let's call it G. Okay, so since we have to frequently use this expression, so there's also you can say a compact way of writing this. Okay, rather than writing this, it is exactly the same thing, but there's a compact notation. What is that compact notation? That both of these weight matrices, WAA and WAX, they can be combined or concatenated in a single matrix, which we call WA. How they are combined, I tell you in a while, right? Similarly, this A and X, they can be concatenated together, something like this. It is only so that the expression becomes simple, okay, nothing else. So what we do, we combine these two matrices in a single matrix. I will tell you in a while how. And then we also concatenate AT minus 1 and XT in a single vector. And then we multiply so that now our expression is relatively simple. So it's exactly the same thing, just a different way of doing it. Now let's see how we are actually doing it. Let's say that your input is say 10,000. Okay, we are dealing with maybe words, so we have a vocabulary of 10,000. So you have 10,000 neurons in the input layer. X is 10,000, and suppose the hidden layer is 100 neurons. Okay, so hidden is 100 neurons. So it means that WAA, which is my weight matrix from hidden to hidden, this is a matrix of 100 cross 100, just like it was 4 cross 4 in the previous slide. Similarly, WAX, it would be 100 cross 10,000. Okay, this is the same, you can say, information as previous slides, only the number has changed. It is more realistic now. So when we say combine these two matrices, what we say, we have WAA, which is 100 cross 100. Okay, and we have WAX, which is 100 cross 10,000. Okay, so you have this matrix, you have this matrix. So what we do, we concatenate them together in a single matrix, right? And this matrix is 100 cross 10,000, 100. Okay, the rows remain 100, the column are 10,000 plus 100. Okay, so now it is a big matrix, and I will just put a separator that this is a big matrix, but we know that the first part of this matrix is actually AA, which is 100 by 100, and the second part of this matrix is 100 cross 10,000, which is WAX. We have simply concatenated them in a big matrix. Similarly, what is this? The A is basically, you can say, your output of hidden layer. Since you have 100 neurons, so you have 100 values like this. Okay, so these are 100 values. And X is your input, which is 10,000 values. So we have concatenated them, and we have a big vector in which you have like 100 values here, and then you have 10,000 values here. Okay, so this is 100 and this is 10,000. Now you see, when you will multiply them, nothing will change. Okay, if you understand matrix multiplication, this part will be multiplied by this part, and this part will be multiplied by this part, and then they are actually added together. So whatever operation we were doing here, it is exactly the same thing. The only difference is that now we have simplified our expression so that we don't have to repeat it every time, and our expression would be much simpler. Okay. So now let me show you exactly the same thing on our lecture slide so that you can do a recap. So as I told you that these two expressions, they have been combined in a single one, where this WAA is a concatenation of two matrices. This one is from hidden to hidden, and the second one is from input to hidden. And we assume that if we have 100 hidden neuron, so it means that WAA is 100 cross 100. And if we assume that input is 10,000 dimensional vector, so our WAX is 100 cross 10,000. So when we concatenate them, so in the first part of the matrix, we have this. In the second part, we have this. Okay, so nothing has much changed. And similarly, this expression is actually concatenation of the vectors. Okay, so this AT minus 1 is the output of hidden layer. So you have 100 values here. X is 10,000 values. So you have just one single vector. So when you will multiply this matrix with this vector, so actually WA is multiplied by AT minus 1, which was also happening previously. And this part of matrix is multiplied by XT, which was also happening previously. Okay, so just you can say another way of writing it, which is you can say much more simplified. Okay, so now from the perspective of, if we summarize our discussion so far, so you see what are the parameters to learn in this case. We have to learn this matrix, we have to learn the bias. Okay, and of course how many bias values we have, equal to the number of hidden neurons. If I have 100 hidden neurons, this BA is actually a vector of 100. Similarly, these are for the hidden layer. For the output layer, we again have a weight matrix and we have a bias value depending upon how many you can say neurons are there in the output layer. And G1 and G2 are two activation functions which depend upon the type of problem you are solving. Okay, so now you see, when you will, if you happen to browse some literature on the recurrent neural network, you will see many different notations, but they all actually mean the same thing. For example, this, if you look at this particular illustration for the first time, it looks something very complex. Okay, but actually it is exactly the same you can say RNN which we have just discussed. It is just, you can say, another way of representing it. So if you slightly try to you can say interpret it, so you see AT minus 1 and WAA, they are being multiplied. So you are multiplying WAA AT minus 1, you are multiplying AX with the input. Okay, so both of these are multiplied, which we also did, and then what you are doing, you are adding them, and you are also adding bias to it. So actually this one is this thing. Okay, you add these three terms together, and then you apply an activation function G1, so you get AT. So it's fairly simple. Similarly, if you want to do it for the output, what are we doing? AT is multiplied by WYA, which is the output matrix. Then you add bias to it, and then you apply some activation function to get YT. Okay, so you see it's fairly simple. It's exactly the same expression that we have been writing, but just a fancy way of making an RNN, right? So don't be confused by the change of notation. All of these will actually map to the same thing. Okay. Okay, so now let's, after all that preamble, let's formally define an RNN, right? So we can say that RNN is basically for sequential processing of sequential data. So it will take some input, process it through multiple timestamps and hidden layer, and produce the output, right? And as we discussed, that the compact way of representing an RNN is this, where you have an arrow leaving and entering the same step, same you can say state, but this arrow has a delay. Okay, this arrow is delayed by one timestamp. Means you calculate something and then you feed it at the next timestamp. And please do remember, when you see these single neurons, this is not a single neuron. Okay, for example, input is 100, so these are 100 neurons. Hidden layer is 50, there are 50 neurons here. If you are solving a digit classification problem, you have 10 neurons here, right? But since when we are drawing, we also have to draw on the time axis. So if every time we start drawing the complete architecture, it will become very complex. That is why we have this compact or encapsulated way of representing an RNN. Okay. So you see, as we discussed earlier, there are different problems you can solve where one of the input or output is sequential data, or maybe both are sequential data, right? So the discussion we'll do is more for the most generalized case where the input is sequence, output is sequence, there are multiple timestamp and multiple hidden layer, right? Because this is the most general form of an RNN. Later, you can simplify it. For example, if only input is sequential or only output is sequential, or you have only one hidden state, then things would be very easy, right? So now you see in this particular illustration, this red is actually showing you the input. It is the same convention, I'm just repeating it. This green is actually showing the output. And these two are actually your hidden layers. So in this case, we have two hidden layers, okay? On this axis, we have time, and on this axis, we have depth. Okay, so as you go towards the right side, you are basically you have time means that if you have three words, first word is t1, second word is t2, t3, and so on. So that's why we say it is time, right? So now we have to see functional dependencies. Now what does it mean? That given a hidden state or an output state, it is dependent on what previous, you can say, state, right? So as I'll show you in the next slide, any, you can say, hidden state can have maximum of two functional dependencies. And we have a slight difference that whether we are talking about first hidden state because it is connected to the input, or we are talking about any hidden state after the first because it will not be connected to input, right? So the first hidden state is slightly different because it is connected to input, and the subsequent hidden states are not connected to the input, right? That's why there's a slight difference. So let's see this. Maybe rather I can draw it so that you understand it well, slowly rather than directly showing it to you. Okay. So maybe let's suppose we have this is input. Okay. Rather, let me draw it at the bottom so that we have space for the hidden layers. So let's assume this is our input. Okay, this red one. And then I will draw a couple of maybe hidden states with blue. So these are my hidden states maybe. And we have two hidden layers. Right, so let's call it layer 1, layer 2. I'm only counting the hidden states, okay? And then we have the output, you can say, layer, which maybe I can draw with a green symbol. Maybe we have output somewhere here. And how things are connected together, let's see. This is the input we are feeding, okay? And then every hidden state is getting some information from the previous hidden state, okay? And hidden state is also connected to previous hidden state, right? So on this axis you have time, and on this axis you have depth. Okay, now let's do some discussion. Okay, maybe this one. Yeah, let's see, maybe let's talk about this particular neuron. Okay, so for hidden state, where we are talking about first hidden state, which is a special case, it is dependent on two different previous states, right? It is dependent on the input, which is x, okay? At the same time step, if I talk of ht at layer L, where L is equal to 1, okay? We are talking about first hidden layer. So it is dependent on what? It is dependent on this input at the same timestamp. Let's say it is t, and this is ht. And it is also dependent upon the hidden state at the same level, but at t minus 1. Okay, you see, because this arrow, this green arrow, it is the same layer, means hidden layer 1, but t is t minus 1. So it means it is dependent on xt, and it is dependent on h t minus 1 at the same layer. Okay, I am using two notations. L is for layer, t is for time. Okay, so for the first hidden layer we have this. Now, but if L is greater than 1, it means if I'm talking about this hidden layer, then what is the situation? For example, let's say this one which I am highlighting here, it is dependent on this particular, you can say, neuron, and this neuron. So it is dependent on what? Please see carefully, it can be slightly confusing. It is dependent on the hidden state of the same level, but t minus 1. It means I'm talking about this one. Okay, same level, but previous timestamp. And it is also dependent on this one, which is same timestamp, but previous layer, L-1. So this is actually this one. So now you see the first hidden layer is dependent on input and hidden state at the same level but previous timestamp. And for any other value of hidden state, means other than the first hidden state, if you are talking about second, third, or fourth state, it is dependent on the hidden state of the same level but previous time and hidden state of the same time and previous level. So that's why here you see t-1, here you see l-1, right? So it's slightly tricky, but this is just for conceptual purposes so that you know that it is dependent on which other states, right? So this is the same thing which I told you in detail, that for l equal ones, the hidden state is dependent on the input, means this thing, and the hidden state at same layer, L is for layer but previous time, right? For example, this is dependent on this and this. And for L greater than 1, for example, say this one, it is dependent on this and this. So one of these is at the same level but previous time, and the other is at the previous layer and the same time. Okay, so this is just a notation, right? Similarly, the weight matrices, they remain the same. Okay, you have one weight matrix which is this vertical arrow. This is from input to hidden. Then you have these horizontal arrows at each layer. Okay, so you have weight matrix hidden to hidden in time, right? Because we are talking about horizontal arrow, but you also have vertical arrows here. Okay, so this is also from hidden to hidden, but in depth. Now you see things are getting slightly more complex, that you have a matrix, weight matrix, which is on the time axis. So these horizontal arrows, we are using T, and for vertical arrows, we are using D, because D actually means the depth. Okay, so as we discussed now, the difficult part is over. Now we have some lighter discussion. So you are already familiar with sigmoid and ReLU activation function, right? But in case of RNN, we'll be mostly dealing with 10H. 10H is very similar to sigmoid. The only difference is that just like sigmoid gives you values between 0 and 1, 10H will give you values between -1 and 1, right? And this is the expression for 10H. If you want to convince yourself, you can feed it any value. So whatever values you feed, they will always be in the range 1 to -1, right? So you see, if we don't use activation function, we just take the dot product. So that disadvantage would be that when you are taking the product, so your values can either become very large or very small, right? Because you are not having any check. So since we have time, so you have many multiplications depending upon what is the length of the sequence. So it is possible that you end up with very high values, like you see 400 here or something similar. But when you are using 10H, you are actually making sure that your values always stay within a, you can say, specified limit. Okay, now to further develop our understanding of RNN, we'll do a numerical example, right? Which is rare that you will really find some numerical examples when you see some tutorials on the internet, right? But numerical examples always help to develop a deeper understanding of the concept we are trying to understand, right? So we'll make a character learning model, and for simplicity, we'll assume that our vocabulary has only 4 letters, H, E, L, right? And we are trying to basically make an RNN so that if we feed it some characters, it can actually predict what is the next character. Okay, so it is a very trivial example with only 4 characters, but later we'll extend the same example and it will be able to generate text for us, right? So let's first see this very simple example. This is our vocabulary, only 4 characters. So we are representing them as one hot vector. So H is 1000, then E, okay, then you have L and O. Okay, so these are the 4 characters. Now, what do we actually want? We want that when we feed a character to this model, it should predict the next character. Okay, for example, if the model is trained, I'm assuming it is trained. When I feed it with character H, what should it give me as output? E. Okay, assuming it is trained correctly. Then when I feed it E, I expect it should give me the next character, which is L, then L, and then eventually it gives me a meaningful word, which is hello. Okay, so this is basically what we want. Of course, it is not trained yet, right? So this is something we want to do. Or you can say predicting a character from only one character is difficult. So let's say I feed it with maybe 4 characters and it should predict the fifth one. Okay, maybe if I give it H, E, L, L, it should predict O. This is more realistic, right? Because you see, just by looking at a single character, it is difficult to predict what is coming next. On the other hand, if you see a sequence of characters, maybe if I show you 10 characters, it is easy for you to predict the 11th character. Okay, so we say, okay, let's keep it slightly simple, that we will feed it 2 or 3 or 4 characters, and then we'll see what it predicts as the next character. Okay, so it is exactly the same thing. We will be feeding character by character, and we will be computing the hidden state for every character, but we will compute the output only when we want it. Okay, just like there was a question a little while back. So now that will also be, you can say, answered once again, that it is up to us that when do we want to compute the output. Okay, so now let's rewrite those formulas with you can say actual notation, right? So it is the same formula: input multiplied by a weight matrix, previous hidden state multiplied by WHH, right? So you see, whether you call it A or H, it is the same thing. Okay, A is activation, H is hidden state. So it's up to you. Since previously we had only one hidden state, so I was using this term A. Now we can have multiple, so maybe I will be using H, and I sometimes I'll be using the superscript to tell the layer number, right? But for this example, we have only one hidden layer, so we don't need this superscript, right? So please do not think what is this H. This H is actually the same notation which was A previously. We are just we have changed the variables just to be consistent with the rest of the terminology, right? Okay, so this is our expression for the hidden state, which is the same thing except for the change of A to H, and this is our expression for the output. Okay, now we know what is X. X is a vector of size 4 because we have a vocabulary of 4. Okay, so this X is a vector of 4. And what is the size of hidden layer? We have to choose it. Okay, so you say, okay, in the hidden layer I will have 3 neurons, 4 neurons. It's up to you. So just to keep it slightly different, I have chosen it to be 3 neurons. Okay, so what the steps I will follow, for your reference, I have listed them in the slides as well, so that if when you are revising, you get to know all the steps. But I'll be performing them, so that's why I'm not reading those out, because when I perform them, you will actually get to know what we are doing, right? So now this is a very, you can say, detailed example. So please see it carefully. It will help you understand this topic very well. So you see, we draw a neural network like this, RNN like this. But for understanding, I am drawing it complete like this. Okay. Now we have 4 neurons in the input. Why 4? Because I have 4 characters in my vocabulary. Okay. So the input is 1 hot encoded. So I have a vector of size 4. Why the output is 4? Because I'm also predicting a character as an output. Okay, and character will be again be represented in 1 hot representation. So I have 4 possible characters. That's why output is also 4. Okay, so input is 4, output is 4, because our vocabulary is of size 4. Now in the hidden layer, you can choose any number of neurons. For this example, I have chosen 3 hidden neuron, because we have to do numerical computation. You can choose it to be 2, 1, 5, 50, anything that you like. Okay, now see what would be the weight matrices. So you see, previously we just draw an arrow. Actually, the connections are like this. Okay, so there are 3 into 4, 12 connections. So it means your weight matrix, which we call WXH, means input to hidden, it is 3 cross 4, and this is that matrix. 3 rows, 4 columns, just some random values. Okay, what would be the WHY? Again, you have 4 neurons here and 3 neurons here. So you see, everything is connected to everything, 4 into 3. So this is 4 into 3, which you see here, right? So it makes sense. Now things are getting together. What is WHH? Now, what is WHH? You will also have, at the next time step, you again have the same architecture repeated here. Okay, so WHH is actually this horizontal arrow, means these 3 neurons are connected to these 3 neurons. 3 by 3. So this is 3 by 3, WHH, hidden to hidden. H means hidden, so hidden to hidden. And how many bias values, how many neurons I have in the hidden layer? 3. How many bias values I need? 3. How many bytes I will need in the output layer? 4, because I have 4 neurons. So it is exactly the same thing which you already know from your previous, that for every neuron you have a byte. So that's why DH is a vector of size 3. Okay, now you see, this notation where we have this loop is not very easy to follow. So as I keep telling you, that in the beginning, it's a good idea that you unfold your RNN. Unfolding means that rather than just using this loop, If you are feeding it three things, you just draw it three times. Okay, so for example, if we are feeding it three characters, so I am repeating the same thing three times. Okay, so that it makes sense to me and I can easily understand, because it is difficult that you do the same thing in this particular notation which is on the left side. Okay, now again, an important thing is that the matrix you see here, the matrices WHX, we just saw that it is 4 cross, it is 3 cross 4. This one is 3 cross 3. Okay, so please remember, it is the same matrix that you have at each timestamp. If WHH is 3 by 3, the same matrix you are using here. Okay, with every timestamp, matrix will not change. Similarly, when we say WHY or WHX for t minus 1, t plus 1, or depends how many, no matter how many timestamps are there, exactly the same weight matrix is used. That's why we say that weights are shared across time. Okay, this is what it means. Okay, anyways, now let's start doing some computation so that we know what we are doing. So you see, this is the first character h, we are feeding it to the network. H is 1000, we are feeding it here. Okay, you have a weight matrix here, wxh, you multiply wxh with this vector. Okay, whatever matrix you have here, you multiply it with this, just like you do in an MLP. Now you also have WHH. Okay, but you see, this is the first character, so there is nothing behind it. There is no hidden state previous to the first character. So as I told you, since there is nothing, so we assume it to be a vector of all zeros, right? Because there is nothing preceding this first character. So what we'll do, we have WHH hidden to hidden, which is multiplied by this vector of zeros, y zeros, because there is nothing coming from the arrow on the left. So we get this 0, 0, 0. Okay, 3 neurons, 0, 0, 0. Then we multiply this input, which is h, with this matrix, and we get this. Okay, and so we have computed this, which is actually this thing. We have computed this, which is actually this thing. Okay, now what we need to do, we need to add bis. We also have bis. Okay, this is bis. So we add all of these three together, we get this. Then we apply activation function. So I apply activation function, I get these three values. Now where are these three values? These three values are here. Okay, means in these three neurons, you have something coming from here, which was 0. You have something from here, and then you also had bis. You add them, you apply activation function using this expression. Now you have three values, which are these values. Okay, just some values I have calculated. Okay, now it means this hidden state is giving this value. If I want to compute output, the same values are going here. I can do multiplication and I can compute the output, right? But I say, okay, feeding only one character and predicting is a bit too hard. So I am not computing any output here. Okay, I will compute output maybe after feeding 2 characters or 3 characters. It's my choice. Okay, so now we have this situation. Now it will further clarify your queries. Now, first character has been fed. This is the output coming on the hidden state, right? And now we are feeding the second character. So if it was maybe T0, now this is T1. So we are feeding the first character, sorry, second character, which is E, and this is coming from the previous time. This is H0, and now we'll be computing H1. Okay, so now this is coming from the previous timestamp. You see, previously there was nothing, so we assumed it is all 0. Now we have something coming from the previous time step, and we have the new information coming here. So we'll repeat the same process. Okay, we multiply WHH, this thing, with the previous hidden state, which we computed, right? Then we add bis, this bis is added, and then we multiply E with WXH, which is on the next slide. Okay, so you add all of these three together, you apply the activation function, so you get this hidden state. Okay, and by the way, same thing is going here. Okay, you have the same thing going here. So, but we did not compute output, so that's why I ignored the red part for the time being. Okay, now you say, okay, let's see, let's compute the output. Okay, although you can repeat this process many times before computing the output, but since we have to stop somewhere, so you say, okay, when we feed the second character, let's see what is the output. Okay, so we just computed this, and the same thing is coming here, right? So the expression for output is that you have a weight matrix of 4 by 3, which is WHY. You multiply it by the hidden state HT, which are these three values. We multiply them, we get this thing. You can add bias, so you assume that bias is already added, so we get these four values. So these four values are actually here, four neurons, four values. It makes sense. Now you can apply an activation function, right? Softmax, so we get something like this. If we convert it into one hot encoding, what is the maximum value? This one. So it becomes 1000. 100 was, I think, H. Okay. So now you see, it is saying that if the first character is H, the second character is E, then the third character should be H. Of course, it is incorrect. But why it is incorrect? Because we have not trained this model, right? It is saying that it is H because it is not trained yet. I have just picked some random values and actually, you can say, try to see what it gives me. But once the model is trained, it is expected to give you some meaningful output. But still, if you ignore the fact that the prediction was not correct, at least we know that how things are working, and numerically we can convince ourselves that this is how, why it is 4, why it is 3, why I am getting a vector of size 3 on the hidden layer because there are 3 neurons, why I am getting a vector of size 4 at the output because there are 4 neurons. So everything seems to be convincing that why a vector has this size, why a matrix has this size, right? So there are different notations that you will see in different literature, right? So I'll just show a few of those. So for example, this is the new information, which is our X. This is the prediction, which is H, and it is going back at the next timestamp, right? Similarly, this is again common notation. This symbol shows a neural network. This shows activation function. So you have X coming from here. You are predicting something H, and then it is fed back as an input, but at the next timestamp, right? But the most common notation that you will see in almost 80% of the blogs is this one, right? And why is it so? Because this notation is very easy to understand. Okay, so this one cell which you see here, this is called one RNN cell. Okay, and what is going on in this? You see, you have xt coming from here, which is multiplied by WAX. You have HT minus 1 coming from here, HT minus 1, which is multiplied by WHH. Then you add bias, and then you add all of these together, you apply 10H. And then you get HT, okay, which is going to the next timestamp. Now you see, at each timestamp, we are outputting HT. If you want to connect your output somewhere, maybe here or here, it's your choice. Depending upon your application, you can connect the output layer wherever you want. It's up to you. So that's why normally when you are dealing with RNNs, we don't show the output because output is specific to a particular application. We just draw a sequence like this, and we just put a branch of hidden state. Anyone who wants to connect the output, they can do so, right? So before we move further, if you have some questions or queries, please let me know so that we can discuss. Okay, now let's see basically some common problems which are known problems with RNNs, right? Now you see, mostly RNNs, as we discussed, are used with textual data, although they are used with other types of data as well. But the examples that we'll do mostly, they will be related to textual data, right? So as always, we see that there's a language model in which we are trying to predict the next word. Okay, so for example, we said the clouds are in the, and the model has to predict a correct word here. So you see, using these 5 or 6 words, 5 words to be exact, right? You can predict that, okay, sky should be the next word. Okay, so now you see, uh, who told you that this should be sky? Maybe this clouds. Okay, cloud is actually a hint that this word should be sky. So you see, sky is dependent on cloud. Clouds are indicating that you should fill this blank with the word sky. And you see how many words are in between cloud and sky? 3 words. Okay, so technically you can say that this is the information which is trying to help you, and you are predicting something here. So you can say that the gap between the relevant information, which is this one, and the point where it is needed is small, right? For example, relevant information were cloud, and it is needed here. So in between you have only 3 words, so this gap is small. This is called a short-term dependency, right? That just see this example, that the difference between cloud and, you can say, sky is only 3 words. Okay, so that this is called a short-term dependency. but you cannot always have the same situation, right? So you see someone is writing about himself or herself that, okay, I grew up in France, and then he or she tells about his education and blah blah blah, and then after many sentences they say, I speak fluent, and you have to predict something here. So you see, if you see only this part, I speak fluent, so your model can guess that there must be some language here. Okay, because speak is telling you that this blank should be filled with the name of a language. But what language is it is? That is dependent on this keyword France. But in between, you have many other things. Okay, so it means that the gap between the relevant information, like France, and the place where it is needed is very large, right? You have many timestamp because one word is a one timestamp, right? So this is called a long-term dependency. And it is known that RNNs have difficulties in learning long-term dependencies. Okay, just one more example that some text and you say, okay, someone was a war criminal, and then you have some text and you and should be sent to. So again, if you see only this part should be sent to, so you know that there must be a place here. But what place it is, school or heaven or what, right? It is basically this keyword which is telling you that maybe this place should be a jail or prison or something similar, right? So again, there's a long-term dependency. And why RNNs are not able to handle this, right? The reason is that when you are using the simple RNN, which we have seen, it has local influences. Local influences mean that, for example, if you are talking about this value, it is mostly influenced by the values which are closer to it. Okay, for example, if you talk of this, maybe the initial words may not have much impact on this output as compared to the words which are closer to this one. Okay, so just like this, that maybe you have say 10 different timestamps. So these first three words, maybe they are not influencing this one as much as the words which are closer to it are influencing it, right? And technically or numerically, what is actually going on? Actually, this is called a problem which is called a vanishing gradient problem. Okay, the reverse is exploding gradient, both are the same concept, right? But normally when people explain this concept, they use the terminology vanishing gradient, right? Now, what is it, and why it is not helping us to learn long-term dependencies? You see, just first look at the example of a traditional MLP. Suppose this is an MLP in which you have many hidden layers. Okay, so if you remember, you compute the error at the last layer and then you do back propagation. And if you remember, there was a chain rule. Okay, f a with respect to b, p with respect to c, and so on. So when you are computing the gradient here, you see chain rule will have 1, 2, 3, 4, 5 different terms multiplied together. Okay, now let's assume, let's make it very simple. Let's assume that your gradient is 0.1 always. Of course it will be different values, but I am just explaining it is 0.1. So when you apply the chain rule, this is just a hypothetical example. So you see, if you apply it 5 times, it will become like 0.00001. Okay, and when you will add this to, you will multiply it by learning rate, add this to the weight, so weights will not change because these are very small value. Okay, so you see, your gradient is actually vanishing. Vanishing means it is going close to zero. If you have 10 layers, if you multiply 10 times, so you will have a number like this. Okay, the reverse is exploding gradient, which is like if you have very big values, so they keep on multiplying and the value becomes very big, right? But mostly we talk of vanishing gradient. Okay, so now how does it come into play in case of RNN? In case of RNN, you see time. So if I have a sequence which is very long, my error has to back propagate to all of these layers, all of these timestamps. So if I have a very long sequence, then by the time my gradient will arrive here, it will be almost close to zero. So that's why we say the impact of these on this particular node would be very minimal, right? So this is why when you are dealing with a data in which you have long-term dependencies, rather than using simple RNN, we use something else which is called long short-term memory network, right? Which I'll come to that in a while, right? We'll see maybe after 15 minutes. So, but first we should know that what is the problem, right? So vanishing gradient is basically when the gradient becomes very small, so it does not contribute to updating the weights. Okay. Now we will come back to long short-term memory networks in a while, but before that, let's conclude our discussion on RNN with some examples. Okay. So as we told you in the beginning of the lecture, we'll do one example, which is sentiment classification with RNN, right? And it must be interesting for you that you see a few years back this sentiment classification, people used to do it as an MS thesis. Okay, it was supposed to be a very difficult problem prior deep learning. But today, if you have to solve this problem, you have data. Maybe 5 lines of code will solve this problem. Okay, and it will solve it in a very good way. Means the accuracy that you will get will be very, very high as well. Okay, it's not that you'll be compromising on an accuracy, right? Okay, so let's try to solve this problem with RNN, and let's see how we can do it. So basically, we have some comments on a product, on a movie, anything, right? And we have a rating. Okay, that rating can be binary, whether it is positive or negative, or it can be star, right? For example, the label of this could be 4, 2, 3, 1. Okay, so you see, in this case, your input is a sequence of words. Okay, so the input is a sequence, but output is a single value. Okay, so it is a single value, so we call it many to one mapping, right? Because there are many inputs, a sequence in the input, and a single output, which is one of these labels. So this is a problem of many to one mapping. Okay, now let's say we say, okay, rather than solving this problem with RNN, let's try to solve this problem in a trivial way. Okay, in a very basic way. Okay, so what we do is we say, okay, I have these words. Okay, these words are represented by one hot vectors. I will have an embedding matrix. Okay, from last lecture, word embedding. So I will multiply these one hot vector with embedding matrix. So I will get vectors for every word. Okay, maybe 300 dimension. So what I do is I take the average of all of these vectors. Okay, and I just feed this 300 dimensional vector to a softmax layer, and I try to learn whether this is giving me some results or not. Now, what is the motivation behind this solution? You see, if in your review you are using positive words like good, nice, you can say pleasant. So from your knowledge of word embedding, all of these vectors will be close in the vector in the word embedding space. Okay, so your model will learn that, okay, if you have many many vectors which are having you can say this interpretation, then the review is likely to be positive. On the other hand, if you have words like bad or weak or not pleasant, right, so you will have vectors which are similar, so your model can learn uh, that, okay, these are actually negative reviews. But you see, there's a very obvious problem with this solution. Okay, someone is saying completely lacking in good taste, good service, and good ambience, right? So in this review, the word good is appearing 3 times. Okay, so your model might think, okay, when you will compute the average of all of these words, good is appearing 3 times, so you will have a representation which is inclined towards the positive side. But actually, it is saying completely lacking. Okay, so it means it is actually the reverse. So in such situation, this model will actually fail because it will not be able to classify. So that's why we normally solve such a problem with recurrent neural network, where we feed word by word, a single word at a time to the model. Okay, so you see, we are feeding word by word, and then at the end we have a softmax layer which is giving us the rating or the star from 1 to 5. Okay, and what is this E? This E is actually the embedding layer, okay, to learn word embedding, because this would be in one hot representation. We first multiply it by embedding so that we have an embedding vector, and then this is the embedding vector we feed to the hidden layer. So in this case, this A is actually our same hidden layer, and on this axis you have time, and we just have one hidden layer, so there's no depth, and you see these are output, which is the softmax layer. Okay, so now let's apply this model to perform, you can say, sentiment classification. For that, we have a very famous data set which is called IMDb movie data set, right? It has reviews, okay? And in this data set, there are 50,000 reviews, and the reviews are labeled as positive or negative, right? Only two classes, that whether, for example, this one is an example of a positive review, and this one is an example of a negative review. Okay, so how this data is represented? Basically, they have represented every word by a number. Okay, for example, this number 1 means the most frequent word. 14 means the 14th most frequent word. Okay, and then of course these will be represented in one hot vector. And normally, since when you are dealing with such data, you can have a huge vocabulary. So what they suggest is that they say, okay, we'll pick the 100 most frequent words. Of course, you can remove the stop words like articles or pronouns, right? After doing that filtering, you can say, okay, I'll pick the 100 most frequent words, and I will say, okay, I will take a review of length 500. Okay, means if something is greater than 500 words, I will skip it, and if something is less than 500 words, we'll just you can say pad it so that we have that only 500 words. Okay, so 100 frequent words and maximum length is 500. Okay, so this data set is available in TensorFlow, so you can just write imdb.load data. It will automatically be loaded. Okay, just like mnist. And then you see this is a function pad sequences. Maximum length was 500. So anything which is greater than 500 is truncated, and anything less than 500 is padded with zeros. Okay. Now see carefully the model we are building. The sequential model. This embedding is the embedding layer. Okay, which is learning the word embedding. So this is 100. It means the input is 100, and this is 32, which is output. So it means you are converting every word into a vector of size 32. Okay, so this 32 can be anything. It can be 300. If you want it to be like word to vector, it can be 50. It can be anything. This 32 is actually the size of the vector which you will feed as input to the recurrent net, right? So this is the embedding layer. Then this simple RNN is the name of the layer, which is this one, which I just which we discussed in detail a little while back. Okay, where you are having weight matrices, you have input, you have previous hidden state, you are multiplying them, applying 10H and giving the output. So for that, in TensorFlow, the name of the layer is simple RNN. And what is this 32? This 32 is the number of neurons here. Okay, in the word in our example, we had 3 neurons. Okay, when we were solving that character recognition problem. Okay, so this 32 is actually the number of neuron, and so we have only one hidden layer, simple RNN, and then we have this is our output layer. Okay, activation function is sigmoid because we are solving a 2-class problem, that whether the review is positive or negative. Okay, now a very important you can say information is that, okay, how many parameters this will have. Okay, so maybe we just discuss. I'll just draw here so that you understand. So our input was actually 100. Okay, let me rather do it peacefully on the board, right, so that you get to know in detail. Okay, because this is something important, right? So that's why I'm spending some time on it. So this is your input layer, and this layer has 100 neurons. Okay, and then you have an embedding layer which is giving you an output in the form of 32, a vector of 32. Okay, and then you have the recurrent RNN. Again, it has 32 neurons. Okay, and I will draw it one more time. Okay, this is T0. Let me draw it for T1 as well so that you understand well. Okay, so here again, when we feed the second word, again, here you will have 100. Here you will have 32. And here again, you will have 32. So you'll keep on feeding words, and finally you have one neuron here, because it's a 2-class problem, right? Which is like connected to all of these 32. So I'm just drawing a single arrow. So it is something like this. Okay, now let's start from this first layer. This is the embedding layer. How many connections are there? 32 cross 100. So the total number of parameters in this layer is 32 cross 100. There is no bias, right? Do remember that in embedding layer, there is no bias because we are just learning this matrix. Okay, so if you remember the topic on word embedding, there is no bias. So this first layer has 3200 parameters. Okay. Now let's see this blue arrow and maybe this red arrow. Okay, you have 32 neuron in this layer, which we are calling A. This maybe I can call E, and 32 here. Okay, so it means this vertical arrow which I have drawn in blue, it will be 32 cross 32. Okay, This is one arrow. You also have an arrow on this layer, this one, which is the horizontal one. You have 32 neurons here and 32 in the next timestamp. So it means you also have 32 into 32. And since this is not an embedding layer, we have bytes. How many bytes we have? 32 neurons. So 32 bytes. Okay, so if you add them together, you'll get something close to 2000. I don't remember exactly. I'll show you on the slide. Nearly 2000. Okay. Now the final thing is how many parameters are in this layer? One neuron here, 32 here. Very simple. 1 cross 32 plus 1 bytes. So total is 33. Okay, so what did we come up with? Maybe first layer has 3200 nearly, not nearly exactly. Second layer has something close to 2000, a little more than 2000, and the last layer has 33. You add them together, you will have the total number of parameters for this. Okay, so the tricky part only is the hidden layer, because you need this horizontal arrow, sorry, this vertical arrow as well as this horizontal arrow. But it's fairly simple. You just see how many neurons are there. The same neurons will be on the next timestamp. So you multiply them together. Then you see how many neurons are here, and in the previous layer you multiply them together, and bytes, you have as many bytes values as the number of neurons. Okay. So let's see our calculations and match them with what we have. Let's see if we did them correctly. Okay. So a good way to do this is if you just make it, you do it by hand, you compute the parameters, and then you call model.summary. It will print the parameters layer by layer. So you can compare your computation with what you are getting from the computer. Okay. So now you see the first layer is embedding 3200. Yes, we predicted 3200, very much fine. Second layer 2080, yes, fine. And the last layer 33, yes, we computed 33. So you see it's exactly the same thing which we computed, but you should, if you are able to compute the number of parameters, it is actually an indication that you have a good understanding of the topic, right? Okay, now you see, if I show you this particular model, if I ask you, is it a deep RNN? So you see, it is not a deep RNN because you only have one hidden layer. Okay, just one hidden layer with 32 neurons. So if you want to make a deep RNN, we agreed that depth is actually on this axis. Okay, so this is your first hidden layer, then second hidden layer, third hidden layer. Because on this axis you have actually time. Okay, so when you are expanding the time, it does not mean that the network is deep. Network is shallow, it has only one layer. So if you want to make a deep neural network, you will actually add more layers. Okay, so let's make a deep RNN. Okay, so now you see this is first hidden layer, second, third, and fourth. There is an additional second argument which you see, which is saying return sequences. Now, what is it? This is important. You see, when you do return sequences true, so if this is hidden layer, then these are connected to the hidden layer, which is next to it. Okay, so you see in all the hidden layer, it is true. If you don't supply any value, it is false. By false, it means that you are not computing anything here. And why we are not connecting this to the output layer? Because in this problem, we are only computing output at the last timestamp, right? If you remember that we are feeding something and we are computing output only at the last timestamp. So these are not connected to anything at the last timestamp. That's why we did not provide anything. And once you don't provide anything, by default, it is false. When you say return sequences is true, true means that these arrows are actually connected. Okay, so because if you have multiple hidden layers, we need to connect them to one another. That's why for all the layers except the last layer, you need to keep return sequences true. For the last layer, it is false because we have output only at the last timestamp. This is the reason it is false. Okay, next you see, just like we said, you can have a bi-directional RNN. We discussed it in the beginning that rather than just you can say scanning your input from left to right, you can also have your input scanned from right to left. Okay, so because we said that future information can also be useful in some cases. So what we do is that when we say bi-directional RNN, you just have actually two RNNs. One is scanning the input in this direction, other is scanning the input in this direction. And actually you concatenate the outputs of both of these. Okay, this is actually concatenation. So we discussed previously that it could be useful, that sometimes the feature information can also be useful. So if you want to implement a bi-directional RNN, from the viewpoint of implementation, it is very simple. you just you just wrap this RNN in another layer which is called bidirectional, and rest everything is handled at the back end, right? You don't need to worry that how things are being handled. They will be concatenated, and you will have you don't need to worry that how to parse the input from left to right or right to left. You just use this simple RNN, you put it, you wrap it in a bidirectional layer. So this is, you can say, a simple bidirectional RNN, and this one is a deep bidirectional RNN, right? Exactly the same thing. We just wrap the RNN layer in a bidirectional layer. Okay, so this will actually, in some cases, this can help you achieve better performance. And the last thing for RNN, before we move to the next topic, if you remember, in the topic of word embedding, we discussed 1D convolution. Okay, that on textual data you can apply 1D convolution. So if you are interested in that, you can very easily do that. That rather than directly feeding text, you can introduce convolution layers. So you have, you can say the first layer in text is always the embedding layer. Then this is your 1D convolution. You have 32 filter, and since this is 1D convolution, so you see filter is only 3. We don't have something 3 cross 3. Okay, because it is one dimensional convolution. Then you can apply pooling, you can repeat convolution, and eventually we have fully connected layer. So this can also be used for some text classification or problem, for example sentiment classification, that rather than directly feeding the text, you can also include convolution in your textual data, right? So this brings us to the conclusion of simple RNN, right? So before we move to LSTMs, if you have any question or any comment, you're welcome to share. Thank you.